Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This video, Properties of Infinite Series 2, is the second of 3 videos on the properties of infinite series and is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. It is recommended to view the video Introduction to Infinite Series prior to watching this video. In this video, we'll be discussing the comparison test, the alternating series test, and absolute convergence. We can determine whether a series converges or diverges by comparison to a series whose behavior is already known. The following theorem for the comparison test for convergence holds. If 0 is less than a sub k is less than or equal to b sub k for all k, and the sum from k equals 1 to infinity of b sub k converges, then the sum from k equals 1 to infinity of a sub k also converges. In other words, if our series is smaller, term by term, than a convergent series, then our series converges. Likewise, the comparison test for divergence states that if 0 is less than c sub k is less than or equal to a sub k for all k, and the sum from k equals 1 to infinity of c sub k diverges, then the sum from k equals 1 to infinity of a sub k also diverges. In other words, if our series is larger term by term than a divergent series, then our series diverges. As an example, let's use the comparison test to determine if a series converges or diverges. The sum from k equals 1 to infinity of 1 over k times the quantity of k plus 1. By comparing it to the sum from k equals 1 to infinity of 1 over k squared. This sum is a p-series where p equals 2, which is greater than 1, and as such, the series converges. If it can be shown that 1 over k times the quantity of k plus 1 is less than or equal to 1 over k squared, then the original series also converges. If we take 1 over k times the quantity of k plus 1 and distribute the k, we get 1 over k squared plus k. For every positive k, the only difference is adding another k to the denominator. Then 1 over k squared plus k will always be smaller than 1 over k squared. Therefore, the series converges. For another example, use the comparison test to determine if the following series converges or diverges. The sum from k equals 2 to infinity of 1 over the square root of k times the quantity of k minus 1. To choose the correct series for comparison, we look at the highest power of our variable k. In this case, 1 over the square root of k squared, or 1 over k. Therefore, we compare this to the sum from k equals 2 to infinity of 1 over k. This series is the harmonic series which diverges. Therefore, if it can be shown that 1 over the square root of k times the quantity of k minus 1 is greater than or equal to 1 over k, then the series diverges. First, we take the term inside the radical and distribute the k, giving us 1 over the square root of k squared minus k. Then we can force a k squared factor that will be removed from the radical, giving us 1 over k times the square root of 1 minus 1 over k. This is determined to be greater than 1 over k because 1 minus 1 over k is less than 1 for all k greater than or equal to 1, because by multiplying the square root of this term, it makes the denominator smaller, making the fraction larger. Therefore, the original series diverges. An alternating series is one of the form the sum from k equals 1 to infinity of negative 1 to the k plus 1 times a sub k. In this series, each term will be the opposite sign from the previous term, a sub 1 minus a sub 2 plus a sub 3 minus a sub 4, and so on. It can also take the form of the opposite sign, where the sum from k equals 1 to infinity of negative 1 to the k times a sub k. This series equals negative a sub 1 plus a sub 2 minus a sub 3 plus a sub 4, and so on. This holds where a sub k is greater than 0 for all integers k greater than or equal to 1. In alternating series, the theorem states that if the numbers a sub k, where a sub k is greater than 0, for either alternating series, satisfies the conditions of the limit as n approaches infinity of a sub n equals 0 and a sub k is non-increasing, that is, a sub 1 is greater than or equal to a sub 2, which is greater than or equal to a sub 3, and so on, then the alternating series converges. There are three ways of determining whether a series is non-increasing. First, by the algebraic difference, where a sub n plus 1 minus a sub n is less than or equal to 0 for all n greater than or equal to 1. The algebraic ratio, where a sub n plus 1 over a sub n is less than or equal to 1 for all n greater than or equal to 1. And the derivative test, where f prime of x is less than or equal to 0. As an example, we'll determine whether the following series converges or diverges. The sum from k equals 1 to infinity of negative 1 to the k plus 1 times 1 over k squared. This is an alternating series where a sub k equals 1 over k squared. First, the limit as n approaches infinity of 1 over n squared equals 0, so it meets the first test. Secondly, we use the algebraic ratio test, a sub n plus 1 over a sub n. In this case, 1 over n plus 1 quantity squared over 1 over n squared. This simplifies to n squared over n plus 1 quantity squared. For all n greater than or equal to 1, the denominator will be a larger value, so it is less than 1 for any n greater than or equal to 1. Therefore, the series is also non-increasing and as such converges. The terms absolute convergence and conditional convergence describe the convergence or divergence of a series in which a sub k are sometimes positive and sometimes negative, yet not necessarily alternating. The definition states that the series, the sum from k equals 1 to infinity of a sub k, is absolutely convergent if the sum from k equals 1 to infinity of the absolute value of a sub k is convergent. The idea is, when we have a series that has some negative terms, if we pass to an entirely positive series, and if that series converges, then the series with the negative terms in it will have to converge as well. The theorem states that if the series, the sum from k equals 1 to infinity of a sub k is absolutely convergent, then it is convergent. For example, let's use the absolute convergence test to show that the following series converges. The sum from k equals 1 to infinity of negative 1 to the k plus 1 times sine k over k squared plus 1. To determine the absolute convergence, we take the same sum of the absolute value of the same series. Since the negative 1 to the k plus 1 is either equal to negative 1 or positive 1, taking its absolute value will result in only positive 1, so that the term may be eliminated. Also, since the variable in the denominator is squared, the term k squared plus 1 will always be positive, so the absolute value is not needed. This leaves the sum from k equals 1 to infinity of the absolute value of sine k over k squared plus 1. The largest exponent in our series is k squared in the denominator, so we'll compare this to the piece series, the sum from k equals 1 to infinity of 1 over k squared, which converges. Next, we consider the function, the absolute value of sine x over x squared plus 1. Since the function sine x has a range on the interval from negative 1 to 1, the range of the absolute value of sine x will be from 0 to 1, meaning the absolute value of sine x over x squared plus 1 must be less than or equal to 1 over x squared plus 1. If we compare this to 1 over x squared, since our function just adds 1 to the denominator, it must always be less than 1 over x squared. Since the piece series converges, and the absolute value of sine x over x squared plus 1 is less than 1 over x squared, by the comparison test the series of absolute values converge. Therefore, the original series is absolutely convergent, and by definition, convergent. Definition. A series that is convergent, but not absolutely convergent, is said to be conditionally convergent. As an example, let's determine whether the following series is absolutely convergent, conditionally convergent, or divergent. The sum from k equals 2 to infinity at -1 to the k over k times the natural log of k. This is an alternating series. First, we determine if the series is absolutely convergent. For this, we take the sum of the absolute values. When we evaluate this, we arrive at the sum from k equals 2 to infinity of 1 over k times the natural log of k. If we consider the function f of x is equal to 1 over x times the natural log of x on the interval from 2 to infinity, the function is both defined and positive. So we need to determine if it is non-increasing. We can do this by taking the derivative of the original function. Using the quotient rule, we get x times the natural log of x times 0 minus 1 times the quantity of x times 1 over x plus 1 times the natural log of x all over x times the natural log of x quantity squared. This simplifies to -1 minus the natural log of x over x times the natural log of x quantity squared. Since this derivative is less than 0 for all x greater than 2, the series is decreasing. Next, we use the integral test on the series of absolute values, or the limit as b approaches infinity of the integral from 2 to b of 1 over x natural log of x dx. To solve this, we let u equal natural log of x, making du equal 1 over x dx. When we substitute, we apply the u value to the boundaries of the integral so as to get the limit as b approaches infinity of the integral from the natural log of 2 to the natural log of b of 1 over u du. This gives us the limit as b approaches infinity of the natural log of u evaluated from the natural log of 2 to the natural log of b. From this, we get the limit as b approaches infinity of the natural log of b minus the natural log of the natural log of 2. This limit goes to infinity. Since the integral diverges, the series of the absolute values will also diverge, though this series is not absolutely convergent. Lastly, we determine if the series itself converges. To accomplish this, we have to show that it meets the two criteria for convergence of an alternating series. The first being the limit, as n approaches infinity, of the related function 1 over n times the natural log of n equals 0, which it does. Next, we need to determine that the series is non-increasing. For this, if we set f of x equal to the related function 1 over x times the natural log of x, and find the derivative. We do this using the quotient rule in the previous step and arrive at f prime of x equals x times the natural log of x times 0 minus 1 times the quantity of x times 1 over x plus 1 times the natural log of x all over x times the natural log of x quantity squared. Again, this simplifies to f prime of x equals -1 minus the natural log of x over x times the natural log of x squared. If we consider this on the interval from 2 to infinity, it will always result in a negative number. This tells us that the alternating series is decreasing for all x greater than or equal to 2. Therefore, by the alternating series test, this series converges. And since the original series converges, and the absolute value series diverges, this series is considered conditionally convergent. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.